Okay, I asked you this question at the end of the last video. So I told you you are measuring the bus when the bus arrives with a scientifically super accurate watch. That means, say your watch is up to like nanosecond, microsecond accurate. So, like when I say exact on time means the bus cannot be late even by a nanosecond, for example. That probability is 0. 0%, 0 is the answer, right? Or you may understand it this way. In our assumption, I said the probability is proportional to the length of the time interval. But then, what is the length of one point, right? Exact on time is exactly at noon is a moment. There is no time. There is no time window. It's not a window. It's just one point. So, I said, you can think of a line as a connection of a lot of dots. If you put a lot of dots in a line, then that makes a line, right? So a line is composed of an infinite number of points, dots. And then a line has a length, but each point has no length. If you agree with that, if you understand that, then we can say the same thing here. Probability is length, but a point has no length, 0 length. So the probability on a point should be 0, right? It's weird. It may sound weird, but it is true. I'm not kidding you. I'm not confusing you. It's truth. It's mathematically true and just true. So also it is reasonable if as I said, it is impossible to be perfect without a microsecond error. The bus cannot do that, right? Um, and this is another property of a continuous random variable. This is always true for any continuous random variable because there is an infinite number of outcomes. You cannot assign any probability to each point. If you put some probability for each point, then the sum of the infinite probability would be the sum of the probabilities over infinite number of outcomes would become infinity. So it cannot be 100%. So that's why to make the sum of the probabilities to 100%, and because there are infinite number of outcomes, single outcome cannot have any probability. It's strange but true. So for example, this is true for all the continuous random variables. A tall coffee cannot contain exactly 12 ounces, or you cannot drive a car exactly at 60 miles per hour, or the weight of a salmon cannot be exactly 1 pound. So it cannot be exact. It cannot be perfect. That's impossible. However, what we can define is something like this. Like instead of referring to one point, you can use a line. So always try to think of a line instead of a point. So we are talking about the length. So you should think of a line instead of a point. So for example, you can define the probability that a tall coffee has less than 12 ounces. Less than 12 ounces is a line. It's a it consists of many possible dots. And probability that you drive a car faster than 60 miles per hour. Also possible. And probability that a wild-caught salmon is between 1 and 2 pounds. Like also, So these examples are well-defined length. They have well-defined length, but one point has no length. That's the key difference and the big difference between discrete variable and continuous variable. So based on that idea, we are going to define the probability in a different way. So first of all, realize that probability of one point is always zero. It is always zero, right? So when I ask you what is the probability for a point for a continuous random variable, you don't need any algebra. It's just zero, as long as the variable is continuous, right? So therefore, we have to define probabilities using inequalities. So for example, we are going to define probability using smaller than or equal to or greater than or equal to inequalities. By the way, because one point has no probability, including the endpoint, like smaller than or equal to, and the probability for smaller than is there is no difference. So including the endpoint or not makes no difference in probability. So when I define probability for a continuous random variable, I am going to switch between strong inequality and weak inequality because their probabilities are the same, right? So later you will see I switch between them without saying why. So remember this. And also here we are going to define the cumulative distribution function again. Actually, we defined it in chapter 3 when we study the percentiles. At the time, we had to calculate the cumulative probability. So cumulative distribution function was defined at that time, but now it becomes more important because this is the only way, this is how we are going to handle the probability distribution for a continuous random variable. So not only for percentiles. We are going to define like capital letter F at a point x, at a value x, define this function as the probability of the random variable smaller than or equal to the value. So if you put different values of x, lowercase x, then you are going to get different probability of about x, random variable x. So mathematically, this is the most fundamental way to characterize a random variable. That means, well, like mathematically, if you know the cumulative distribution function, then you can calculate any probability. I'm going to show you that in the following. So, and what that means here is, suppose that you know this function, right? If you know this function, that means you can calculate probability defined in this form. So if you're curious about a probability that the random variable is smaller than or equal to a certain value, that information is already contained in this function, CDF. But then if you're curious, by the way, if you're curious about a probability greater than something or in between 2 points, then how can you calculate that? My answer is mathematically, this is enough. So if you know the CDF, then you can calculate those probabilities from this function. That's what I'm going to show you. So knowing this function is enough, sufficient to calculate any type of probability you want. Let's see. So suppose that like now we are going to consider the amount of tall size coffee at Starbucks. You ordered a coffee and you after getting the coffee, you measure the amount with a very accurate scale. And suppose that you know the CDF at those points. So CDF is known at these 3 points. That means, let me interpret this. So the probability that a tall size coffee contains less than 11.9 ons is only 5%. The probability that a tall size coffee is less than 12 ons is 30%. And the probability that a tall size coffee is less than 12.2 ons is 90%. Right? So this part means it's a probability smaller than this amount. Right? Probability smaller than this amount is given by these probabilities. That's how we read the CDF, the cumulative distribution function. So as I said, it's a smaller than, all the probabilities are smaller than this amount. Then, how can you find probability greater than 12 ons? So, it's pretty simple because we know that probability smaller than 12 is 30%. Then, obviously, probability greater than 12 ons is 70%. By the way, I'm not considering the or equal to. So I didn't say probability greater than or equal to 12 or probability smaller than or equal to 12. Or equal to is meaningless in probability, so I did not mention that part. So as I said, like a strict inequality, weak inequality have no difference in probability. So anyhow, the idea is probability smaller than implies probability greater than. So this is the idea. We know the whole line has 100% probability, and we measure the probability from the smallest part up to a point. That's cumulative probability. Once you know this, the other part is automatically calculated by taking 100% minus the cumulative probability. So probability greater than something can be calculated using the CDF, which is 70%, right? So this is an example showing that the CDF contains all the information you need. Let me ask you another question. So CDF is given like this. You know this. Then we would like to calculate the probability between 2 points. So 11.9 and 12.2. What is the probability that the actual amount is in between these 2 points? How can you calculate? Guess it? Try it by yourself. If you're smart enough, you will see the answer quickly. So the idea is like this. So probability, we are calculating probability between 2 points, lowercase x, lowercase y. But what we know is probability smaller than y and probability smaller than x. And then we are looking for this length. Still, we are trying to understand the probability as a length. We are looking for this length. But what we know is this longer one and this shorter one. So automatically, their difference is the length between those two endpoints, right? So we know from the smallest point to y, and we know from the smallest point to x. So the length between x and y is their difference. So you can just take the difference. So in our information, 12 like 90% of the coffees would have less than 12.2, and only 5% of coffees would have less than 11.9 ons. So their difference 85%, you can say that 85% would be greater than 11.9 but smaller than 12.2, right? So out of 90%, 5% is even smaller than 11.9. So the other side is this one. So 85%. So what you can see from these examples is that, as I said, if you know the cumulative distribution function, then you can calculate this probability, a probability on an interval with two endpoints. Also, you can calculate probability defined this way, probability greater than something. Of course, the CDF itself provides information about probability smaller than something. So these are three types of probability you basically need. So, and the CDF can calculate them all. So you only need the CDF. So the CDF is the most fundamental way to characterize probability distribution. So that's what I'm saying here. So, okay. So in the next slide, in the next video, I am going to extend this idea to another dimension. So far I explained as if the probability is a kind of length, but actually that's not true. That was just an introduction, an example for introduction, but we have to expand our understanding to the two-dimensional space. So I'm going to do that in the next video. See you later.